Good morning, folks. This is Chemistry 132B, Quantum Principles, once again. There's going to be a midterm on Friday. I just sent out an announcement on the Canvas site. Hopefully you have seen that. So hopefully it's self-explanatory. Basically, the midterm exam will be run in the same way as before. The main difference is that we will have the monitor on this time. So it's just to eliminate people who don't play by the rules. And everything else is pretty much the same. So it's open book, meaning anything that is printed on paper is allowed. You can have in front of you. You cannot have additional electronic devices. And because that means that you can look things up. We don't want you to talk to your buddies during the exam. We don't want you to use the internet to look up answers or engage in any form of communication online. That is what we want you to do, which is, I think, very self-explanatory. And that's why we don't want you to use any electronic gadgets, because if you can, then we know that people will and will abuse it. So if you have your notes on your electronic device, please make sure you make printed copies of that on paper so you can have them in front of you. I will tell you again that the exam is fairly self-contained. You don't need to look up formulas. All the formulas are given, they're present. If you need a particular expression of anything, it is on the exam. So you don't have to look anything up. If you are comfortable with the material, if you feel like you get it, then that is enough. We don't ask you to do complicated mathematical calculations because they take time, and that's not what the exam is about. We just want you to see. We just want to see from you, that you get the main basics, the main principles of what we have been talking about. So that is what the exam is about. It's not a test for mathematical proficiency by any means. You don't even need your calculator, I think. No, I don't think you will need your calculator at all. So, you just need to be familiar with the material, and then you should be good to go. That's all. Yeah, so we do use a monitor. If you've done this before, then you may be asked to show some things that you have in front of you. So that is, I think most of you have done this before. So we will do the procedure in the same fashion. You have to show your ID at the camera, and the person there may ask you to show you materials you have in front of you. But it's an open book exam, so you are allowed to have any type of paper stuff in front of you. That's completely fine. The solutions to the practice midterm will be posted probably tomorrow. So you will have a chance to look at that shortly. Okay, are there any questions at this point before I will continue with this lecture, lecture 20? Anybody? Let me know. If you have any questions about the material, please send me an email. If I receive a lot of emails, I may set up an office hour tomorrow at some point, maybe late in the afternoon. So it depends on if there is a need. If there's many questions that remain unanswered, then I'll be happy to talk about that tomorrow afternoon. Okay, so I'll let that depend a little bit on the need, if there is a need. Okay, so in that case, let me start talking about the material of lecture 20. And it is, of course, related to the last stuff we have talked about, which is lecture 19. And in lecture 19, we talked about the variation principle. The variation principle is a very important principle that people use all the time if they do computations of molecular states. What are the energies of the states in a molecule? And the variation principle is used a lot for that purpose. The variation principle is a very useful tool. What it does, it takes a wave function that is an approximate description of the actual wave function. We don't know the actual wave function. Why don't we know it? Because it's too difficult to solve the Schrödinger equation that includes all the interactions between the charged particles. It's too complicated. We don't have analytical tools to solve these problems. So we do need approximate tools. And that is what the variation principle gives us. We can make a trial wave function and then see by changing things in this trial wave function, for instance, coefficients, we can change the coefficients in such a way that we find the lowest possible energy of the system. And that is always a better description than energies that are higher. So we try to find the lowest possible energy, and that is typically a better solution than any energy that comes out higher. So this is one way for us to find very good approximations for the wave functions in molecules. So today we're going to look at this very simple molecule, which is H2 plus, 2 hydrogen atoms together. They form a bond, but it is a ionized species, so it only has 1 electron. So it's 1 electron, 2 nuclei, and we're going to try to look at the solutions that we got on Monday, lecture 19, from the variation principles for this particular case, and then give a little bit more meaning to the numbers or the expressions that we got. Okay, so what we found is something that looks like this. These were the energies that we found with the variation principle. Of course, we find 2 molecular orbital states, psi plus and psi minus. Psi minus has energy E minus, and psi plus has energy E plus. The plus and minus versions of the wave function, of course, are found by adding or subtracting the respective atomic orbitals, right? So this is how we are combining the two. And in the case of hydrogen, the coefficients are the same. Not always, but in the case of hydrogen, they are, because these are identical atoms. So the coefficients that we found in this particular case have the same value, they just have different signs. So there's only 1 electron here, so that simplifies things a little bit in terms of finding the actual energies. What do I mean by that? Well, this is what we found last time. Okay, you can go back to the lecture notes and see that the energies we found through the variation principle is the following. E plus is alpha plus beta divided by 1 plus S. Okay, and then of course the negative version is the same, but with negative signs. And these integrals indicated by alpha and beta are as follows. Alpha has a little I because it depends on what kind of wave function you are integrating over. Okay, so if you integrate over wave function I, then this is the integral that we have to solve. So the wave functions here, the wave function psi I, is the wave function that we are using to compose the molecular orbitals. Okay, so psi I is basically the wave function from the individual atomic orbital. So that is the wave function, and the Hamiltonian is the real Hamiltonian. It's the Hamiltonian that includes all the interactions that are relevant to this molecular system. And as we have concluded last time already, these atomic wave functions are not eigenstates of this new Hamiltonian. So we cannot immediately solve this integral. Okay, so we're going to try to do something about this anyway to see how far we can get. But that is basically what I'm going to try. I'm going to try to give a little bit more meaning to this integral. Beta is given as such. It looks very similar, but of course I have psi I on the left and psi j on the right. And these two are not equal in the case of beta. In the case of alpha, they are. In the case of beta, they are not. Okay, so this is a slightly different integral. And then S is the overlap integral between these two wave functions, psi I and psi j, which again are the wave functions of the individual atomic orbitals, from which I construct the atomic orbitals. So can we say something about the values or the meaning, the physical meaning of these integrals? Because I find these solutions, which is great, but it's just a hodgepodge of symbols. So what does it mean, and what is this? So let's have a look at this. Let's try to look at these integrals and see if we can extract some meaning and maybe some values out of them. So there's two ingredients, of course. There's the wave functions, and there is the Hamiltonian. The Hamiltonian is given right here, as you can see. In general, it is, of course, the kinetic term. That's the first term over here. This is the kinetic energy term. There's only one electron that I have to take care of. All right, I'm not thinking about the kinetic energy of the nuclei because they're steady compared to the electron. So only the electron kinetic energy term is considered. I only have one electron, simplifies things, so there's only one kinetic energy term. And then there is a potential energy term, and that includes all the interactions that are given here. Okay, so first of all, there is kind of a collection of constants here in front, and then there is 1 over Ra, which means, of course, the distance between the electron and the nucleus A, that's given in the picture above. And then 1 over Rb, that is the distance between the electron and nucleus B. So these first two terms is simply the Coulombic interaction between the electron and the individual nuclei, right? And you can see they have the same sign because that is a favorable interaction. It's an attractive interaction. There's a negative sign here in front, as you can see, and that means both the first and the second term here are negative, which means attractive. There's an attractive interaction between the electron and the nuclei. There's another negative sign here, so that cancels out the negative sign in front, which means this is a plus sign. This is a repulsive interaction. Where is it from? Well, the big R here is the distance between the nuclei A and B. Okay, and of course, these nuclei have the same charge. They will repel one another in a Coulombic fashion. So these are the interactions that I have to take care of. There's attractive interactions and repulsive interactions. You can see this repulsive interaction is very important because if there's no electron in between to kind of offset the repulsive interaction, then this molecule will never form, okay? Because these two atoms don't like to be together. So there has to be an electron there that sits in between to offset this repulsive force. Okay, so what I'm going to do now is I'm going to take this Hamiltonian and I'm going to calculate these integrals, alpha and beta. Okay, and what I'm going to do is I'm going to first calculate alpha A, which means this I here, this I right here, is the, so I runs from A to B. Okay, so A, comma, B. This is my strange bracket here. AB simply means atom A and atom B, the wave function on atom A and the wave function on atom B. So if I put an A here, that means that these become the atomic wave functions of atom A. Okay? So that's the first integral I'm going to calculate. And I'm going to do the same thing for beta, where I put this as an A and this, of course, as a B. Right? So those are the two integrals I would like to have a closer look at. So here we go. Oh, before we go, I'm going to simplify things just a little by taking all these constants and call these constants simply J naught. Okay, so that means we don't have to repeat this. We just write J naught, and that looks a little cleaner that way. Okay, so alpha A is what I'm going to calculate. And so I'm going to sandwich now the Hamiltonian, the new Hamiltonian, in between these atomic wave functions that belong to particle A, atom A. And we know that psi A is not an eigenfunction of this new Hamiltonian. Okay, I hope it's clear why, because the new Hamiltonian contains all kinds of interactions of the new system, while the psi A was solved for only the individual atom. That did not include all the interactions. So these two things are not compatible, right? They don't belong to one another. So I can't really solve this right away, right? I cannot just get a simple eigenvalue out and I'm done. I'm getting something else. And that something else is what we're after here. So here is my, I'm going to expand this. Let me walk you through this. Does anybody say anything? Okay. So the first terms here, okay, between parentheses here, this term right here, is from the kinetic energy of the electron, and this is J over RA. Remember the RA term of the potential energy? That's what I'm going to put together. Why am I putting these two terms together? Because this is the kinetic energy term of the individual electron, and this is simply the attractive force between the electron and atom A. So this is really the solution that I was looking at previously, because it's the interaction of an electron with nucleus A and its kinetic energy. So that is simply an individual atom. So the whole first term here is equal to my previous problem. There are no additional interactions. These are the interactions of the individual atom. That's good, because I know that this operator here between parentheses is really our previous Hamiltonian that belongs to this wave function. So this wave function is an eigenfunction of the Hamiltonian in between parentheses. Okay? It's just these extra terms that come after it that are not part of the original Hamiltonian. So I separate these out. And the first term that I'm separating out is 1 over RB. That is the interaction of particle that came from A, but is now interacting with the second nucleus. Okay? And it's interacting as 1 over RB times this J naught term, this hodgepodge of constants that indicates the strength of the potential energy interaction. And then the last term here is the repulsive term between the two nuclei. That's 1 over R times J naught. And I can take that out of the integral because this R here, this capital R, doesn't depend on the position of the electron. And these two wave functions here are electron wave functions. Okay, so that means I can take this term out of the integral and just put these two wave functions together, basically having an overlap integral of the wave function with itself, which is going to be 1. Okay, so that's good. That's good news. So let's clean this up a little bit. What I'm getting is the following. The very first term here is simply the energy of my 1s, my unperturbed 1s wave function in hydrogen. Okay, because that's what the first term says. No additional interaction, just a clean hydrogen atom by itself. I know the solution to this problem. It is simply E1s, the energy of the 1s orbital. That's the ground state of the electron. The second term is really this term right there above it. I haven't changed it yet. Okay, so it's an integral times J naught. The integral is psi A sandwiched, and in the middle there is RB. Okay, and then there's this last term plus J naught over R. So I'm going to clean this up just a little. I'm going to say it looks like this, where this little j here with no naught is simply the integral that is encircled here above in green. So what I have is the energy of the 1s orbital, the unperturbed orbital, plus an additional energy contribution because of the repulsion of the two nuclei. So the energy is going up a little bit. It becomes less favorable because of repulsion of the two nuclei. And then subtracted from it is a favorable interaction. That is the interaction that the electron now has with the second nucleus. So the electron is also attracted to the second nucleus. That leads to an energy lowering of the whole thing. So this term here, in between, in this circle here, is really the electron density from A interacting with the second nucleus. That's what it means. That's what the J means. Okay, so this is what I'm going to leave. I'm going to leave this for now. This is pretty manageable, right? Each term tells me something, tells me about a contribution to the total energy. The original unperturbed one, all the way to the left, then a repulsive term, which is bringing the energy up, and then a small negative term that's bringing it down again by a little bit because of a favorable interaction of the electron with the second nucleus. Okay, so that's alpha. Now beta. Beta is this integral. I'm going to do exactly the same thing that I did above. So I'm going to write it out. Here it is. I'm going to do the same thing as above, where you will see that instead of having this psi A here, it's going to be psi B. Okay, so this A here that I'm encircling with my cursor right there, it's going to be a B. But that's fine because this is a hydrogen atom as well, which means that it is can still operate on this wave function and generate again an E1s. Okay, because these are two hydrogen molecules, two hydrogen atoms, and so each atomic orbital will generate the energy E1s, right? Because that's the ground state of an individual hydrogen atom. So that is coming out nicely. That means I can take the energy E1s out of the integral, and I'm left with this overlap integral here. Now this overlap integral is not zero. Remember, we call that S. S is not zero necessarily. Sometimes it is, sometimes we make that approximation, but in general it's not. And that's because these are two wave functions from different systems. And so they're not necessarily part of a complete set because they're from different systems. So I simply call it S. Then the second term here, which looks a lot like the term J up here, with, of course, the important difference that now I have a B instead of an A. So what does that mean? That means I have A on one end and B on the other end of the integral, with in between a 1 over RA, which means the distance between the particle and the nucleus A. AB means the overlap charge density is interacting with the nucleus of particle A, of the first hydrogen atom. Okay, so the A and B here on the left and right indicate the charge density of the overlap. The overlap of the two particles generates multiple opportunities for the electron to be in between the two atoms, and that charge density that it creates is interacting with particle A. That's what it means. And then the last term is what I'm seeing here. This term right there looks very similar to the term up here, with the important difference that there's now a B. That means that this guy is called S. This whole integral I can call S. All right, so what I'm going to do is I'm going to put all the S terms together. The two S terms are the E1s plus J naught over R. They both are multiplied by S. So I'm going to combine them. And then minus this integral right there, which I can call K. And K and J are related. J, of course, is the charge density of particle A interacting with nucleus B. And K is the overlap charge density, interacting with particle A. Okay, so this is what I'm getting. So I'm going to take these results and then put it into this formula right here. This is the general formula with alpha and beta, and I'm now having some expressions for alpha and beta. So I'm going to put them in and see what I get. Okay, so for E plus, after substituting the newly found alpha and betas, this is what I'm getting. Okay, so I'm getting E1s, which is the original unperturbed energy, plus a repulsive term, and then minus the term that depends on J plus little k over 1 plus S. Okay, and the second energy, which is E minus, is also the energy of the unperturbed atomic orbital of hydrogen, plus this repulsive term, and then again something subtracted, which is now J minus K. So there's a minus sign here, and also in the denominator, I see a negative sign. Okay, so that's the difference between E plus and E minus. The first two terms, as you can see, are the same. This term and this term are the same. The original unperturbed hydrogen energies, the ground state of an electron in a hydrogen atom, that's this energy right here, and then something added to it for both E plus and E minus. So both energies go up, and then E plus goes negative with this amount, and E minus is going to go also negative with this amount, but this amount turns out to be a negative number, so in the end it goes up. This is what results in this picture. Okay, this is what we get. This is what we already saw, and we notice that E plus is going to go down because of the term right here. Okay, this term will bring it down. Okay, so that's basically E plus, and E minus, this term will bring it up. Okay, because this term is actually a negative sign, so it goes up even more. That's why E minus is higher then E plus is low. This is not symmetric, as we have already concluded. It's not a symmetric scenario here. It is an asymmetric case. E minus is way higher up than E plus is down, okay? And if you fill out numbers here, you can see that. It comes out that way. So just to summarize here, this J naught over R is the repulsive interaction of the two nuclei. It's positive. It's the same for E plus and E minus, and it adds to the overall energy. So both E plus and E minus will go up because of this repulsive interaction. Second point is that the integral J, as we have concluded, measures the interaction between the electron density from particle A with the nucleus B, or vice versa. Right? That's the same thing. The electron density on B with nucleus A. They both give a J. Okay, so this J is an integral. We call that J, okay? We don't know exactly what it is. We have to compute that with a computer. We cannot do it by hand. It's not an analytical expression, but we can evaluate it numerically and get some sort of an idea of how big that is. Okay? K, as we have concluded, is the overlap charge density with either A or B, either the nucleus A or B. So it's the overlap charge density that is interacting with nucleus A or nucleus B. Okay, that's K. So K, like J, we have to compute with a computer. These integrals cannot be solved analytically, and but still we can get some numbers out. The S is generally smaller than 1. J is generally larger than K, and that leads to the splitting of the bonding and anti-bonding orbitals that are uneven, as shown over here. Okay, so the anti-bonding is split more than is the bonding orbital. That follows from this analysis. Okay, so what we've done here is we've given some meaning to these alphas and betas, so we have some better grasp of why E plus is going to go down, why E minus is going to go up, and what kind of interactions cause that. Okay, what is the origin of this? That is basically what this exercise has allowed us to do. Okay, so with this established, we're going to look at the molecular orbitals themselves and look basically a little bit at what they look like in space and what kind of symmetries they have. So here is the sigma bonding orbital. Of course, that means two orbitals smushed together. There is a charge density in the middle, which is substantial. That causes the bonding. It basically offsets the repulsive interactions from the nuclei and therefore enables the molecule to stay together. What is this gerade here? Gerade is a, that is a German word. If you are German, then you may recognize this. Gerade, that's how Germans say it beautifully. Gerade means equal. That means these two orbitals are equal in a way. You can see that they have the same kind of color, but what it really means mathematically is that there is inversion symmetry. So if I draw an arrow through the middle, that's the inversion point, from one end to another end, doesn't matter which way the arrow goes. You start somewhere on the left, you go through the middle and you go to the right. Right? Okay, that's what inversion symmetry means in this particular case. If you do that and you get the same sign of the orbital, meaning the phase of the orbital is the same on the left and on the right, that is called gerade. That means equal, and that means that this is a sigma G. Okay, sigma G is a gerade orbital, gerade molecular orbital. It also means that we have something called ungerade, and that means, of course, that the two orbitals have opposite signs. That means they destructively interfere in the middle. There's no electron density to offset the repulsive interactions between the nuclei, and therefore this is an anti-bonding. This is a very bad situation, of course, because that means that the two atoms are being pushed away from one another. There's anti-bonding character. It's worse than having no interaction. It's an anti-interaction, pushes things apart. So this is ungerade. So sigma ungerade is an anti-bonding orbital. Sigma gerade is a bonding orbital. Here are our orbitals again, E plus and E minus, but in this case, I'm going to look at H2, not a plus. So there's two electrons, And both of these electrons, of course, are going to accommodate the lowest orbital that is available, the lowest molecular orbital that's available, and that is the 1 sigma Gerade. Okay. Now this 1 here, just to make sure that people recognize that, doesn't mean that it comes from the 1s. Okay. This 1 in this kind of way of writing simply means that this is the first sigma I'm considering. Okay. Somewhat arbitrary, but that's really the notation. 1 sigma Gerade means the first bonding sigma orbital that I'm seeing is what I call 1. And this one here means this is the first ungerade that I'm encountering. 1 sigma ungerade. So the anti-bonding is ungerade and the bonding is gerade, as you can see here. If I go to helium, helium-2, it's the same story, pretty much the same molecular orbitals in terms of their symmetries. The lowest one is gerade, and of course the higher one is the ungerade. It's the same kind of formulas, and the energies are going to be slightly different, remember, because this is helium, has a different nuclear charge. It also has an electron-electron interaction. So these energies will be at different levels than for hydrogen, but they are going to be equal relative to one another because these are 2 helium atoms. So overall, it looks very similar, although the numbers are going to be slightly different compared to the ones from hydrogen. Here I have a total of 4 electrons, so 2 go into the gerade, 2 go into the ungerade. So helium-2, of course, is not forming a molecule because of the anti-bonding character. Because the anti-bonding character is higher up in energy than the bonding character is low in energy, meaning that helium-2 really doesn't form. Okay, it does not form because it has more anti-bonding character than bonding character. So, and you know, most of us know that helium-2 is not a stable compound for this particular reason. So atomic orbitals that have the same symmetry and are close in energy, they have the propensity to mix and produce molecular orbitals. I'm just reading the sentence aloud, but that's really the message of this slide. So we have seen that two s orbitals of hydrogen and helium can come together and form a molecular orbital, but any orbital from 2 atoms, okay, so atom 1 and atom 2, if the orbitals from each of the atoms have the same symmetry and they are close in energy, they have an opportunity to mix and form molecular orbitals. Okay, so here's the energy level diagram for typical multi-electron atoms, and we can state the following: if you have 2 1s atoms, that 1s atomic orbitals that come together, they can of course mix to form sigma bonds or sigma molecular orbitals. And the 2s can mix with the 2s, so 2 atoms come together, they both have 2s orbitals. These 2 orbitals can mix between them and form molecular orbitals. They can also form with the 2pz. Okay, so let's say 2s from one atom can mix with a 2pz of another atom, as we will show you on the next slide. You can see how that works. And that's because the 2pz is aligned along the bonding axis and therefore has the same symmetry as the atomic orbital of the first atom. So they can form a bond. So 2s of one atom can form a bond with the 2pz of another atom. And then, of course, you can have these pi orbitals where you have a 2px of one orbital mixing with a 2px of another atom. Okay, so 2px of one atom, can bond with a 2px of a second atom. And the same holds for the py. So they form, in this case, pi orbitals. We've seen that before. So let me just show you those pictures because I think it's important to have these pictures in mind rather than just these sentences. 2 pz orbitals, they can, of course, come together and form a bond on axis. So this 2pz, if you flip it around and this yellow part sits here on the left, then they can form a bond together that looks like so. That is a sigma Gerade. Okay, so the 2pz orbitals form a sigma G bond, sigma Gerade bond, because the symmetry is a Gerade symmetry here. The anti-bonding version is really if this blue part is trying to come together to this yellow part, means opposite phases. I get a node in the middle, and that is a ungerade, okay, because I basically have a change of sign if I go through the middle, through the inversion point. That is a sigma ungerade. So the two pz orbitals can form sigma bonds, both Gerade and ungerade. This is a bonding between a s orbital, here in this case a 2s, but this could also be a 1s of hydrogen, for instance, with a 2pz from carbon, okay? That's a very common bonding pattern. If the sign of the s orbital is the same as the sign of the 2pz lobe on this end, then they can form a sigma bond on axis that is Gerade. And the opposite, of course, is also possible. So when this yellow color sits on the left side, then they come together and form a node in the middle, and that is an on-axis bond. That's a sigma bond, therefore, but it's ungerade because of the different phases on each end of the node. That's a sigma ungerade. These are the pi orbitals. I think we're all familiar with this already, but let me show you anyway. You get 2px or 2py come together, and there's overlap of the charges from each end, forming a higher electron density in the middle, but it's off axis. That's why it is pi. The interesting thing with the pi orbitals is if you look at the bonding one, and you go through the symmetry point here, the inversion point, from the left to the right, you actually go to a different phase. You see that? So the bonding pi is ungerade. Pi u is an ungerade bonding orbital, same for the 2py. And if you look at the anti-bonding pi orbital, where there is a nodal plane here, okay, then if I look at the inversion symmetry, I go from a particular sign to the same sign through the inversion point. So that means pi Gerade is an anti-bonding orbital. Okay, so in sigma speak, the sigma u was the anti-bonding, but now it's the bonding in pi, and vice versa, right? The same is true for the 2py. Okay, so what do we get? Well, we get the following. If you look at, forming molecular orbitals between period 2 elements, the 2 atoms from period 2 come together, let's say 2 carbon atoms, then initially I can think of the following way in which these molecular orbitals will combine. Okay, so for the 2s, because I'm only considering the shell of the valence electrons, which means I'm not considering the 1s electrons of, let's say, carbon in this case, because they form a closed shell. So only the open shell levels are considered here in this MO diagram. This one here is the first sigma that I'm encountering. So even though it's formed from the 2s and the 2s from the atomic orbitals, the molecular orbital, the first one I'm considering is called 1. Okay, so that's confusing sometimes, but that's just the way it is set up here. So one sigma G Gerade is the bonding sigma, and then the ungerade is the anti-bonding sigma from the 2s atomic orbitals. Then I can form the 2pz orbitals, an on-axis sigma bond. So 2 sigma G, this 2 here means it's simply the second type of sigma bond I'm encountering. The first one was over here below, the second one is the one up here. And then I have these 2px and 2py that form pi bonds, and because it's the first pi bond I'm encountering here, it's called 1 pi u for the bonding, 1 pi g for the anti-bonding. Okay, so this is really the simplest way in which I can construct molecular orbitals for the atomic orbitals of period number 2. However, there is a big disclaimer here, and that is the following. The 2 sigma g and the 1 sigma u, they do have the same on-axis electron density and symmetry. Okay, so when they get very close in energy, orbitals that get very close in energy and have the same symmetry can split. Okay, they can interact, they can interfere with one another. And every time wave functions interfere with one another, what happens is there is a splitting happening with a certain efficiency. So what will happen if these two get very close, that you basically see that this state will go up and this state will go down. Okay, this is called SP mixing because of the molecular orbitals that form. Okay, so that happens in the second period. It's a very well-known effect, and you may have heard of it. So the effect of that is the following. So what I'm seeing here is that these pi orbitals from the 2p atomic orbitals are unaffected because the off-axis symmetries have nothing to do with the on-axis sigma bonds. Okay, so they are unaffected. That is basically the same. But if these two guys come together, they will split, and that leads into the following situation. This 1su goes down in energy, and this 2s gerade can go up quite a bit, to such an extent that it can overtake this 1 pi u. So it can actually be all the way up here. All right, so it's quite a split, as you can see. And it means it reverses the order of the energies of the molecular orbitals. So below here, I still have 1 sigma g, 1 sigma u, but then the lowest energy from the 2p atomic orbitals is 1 pi u, and then the on-axis sigma 2 sigma g. Okay, this is something you may have seen before. When is this important? It is important for those atoms where these two states are very close. And that turns out to be for atoms that are lighter. Okay, for lighter atoms, the 2s and the 2p are closer together than for heavier atoms. So we may expect this for the lighter period 2 elements, and we may expect this not to be the case for the heavier 2p period elements. And that's exactly what is observed. So here you see the period 2 elements forming diatomics, homodiatomics. You see lithium-2, beryllium-2, boron-2, carbon, nitrogen, oxygen, and fluorine. And in the case of the lighter elements all the way up to nitrogen, you can see that this mixing between the sigma from the 2s and the 2p causes this state here, this blue state, which is a sigma state, to be higher in energy than the pi bonding state. You see that? That's true for lithium, beryllium, boron, carbon, and nitrogen, and only for oxygen, with the separation between the 2s and the 2p atomic orbitals is high enough, this interaction is relatively insignificant, so that we don't have the 2 sigma g overtake the pi states. It's lower in energy, meaning the interaction between the sigmas is not as strong as it is for the lighter elements. Okay, so the O2 and F2 are regular molecular orbitals, if you want, and the ones of the lighter elements are irregular, where the 2 sigma g is higher than the 1 pi u. So this is something I believe most of you have seen before, but maybe not in this kind of context where we use these notations. These are the official notations that you may find in more advanced textbooks. So that is where it comes from. Okay, that was it for today. We will continue with this story next week, because now I think we want to prepare for the midterm. So this is basically put on the shelf for now till next Monday. All right, folks, thanks a lot. Let me know if you have questions about the midterm and you'd like to have, kind of an office hour on Thursday afternoon, then we'll set that up.